let's talk a little bit about activation and deactivation as well as directivity. So there are two things you need to consider when you are doing an electrophilic aromatic substitution reaction on a already substituted benzene ring, because the group that's attached to the benzene ring is going to have an effect on the next electrophilic aromatic substitution. So it depends on what that group is. So the R group, that is to say the thing already attached, whatever the identity of it is going to determine where the next group, the E in this example, ends up. So to determine where the E goes, you have to figure out what R is and how it behaves, how it affects the ring. And there are two issues, as I said. One is where it ends up or where it's substituted. Does it, in the case of an already mono-substituted ring, does it end up at the ortho position? Does it end up at the meta position? Or does it end up at the para position? And then the second question that is also important in the terms of synthesis, because we don't want to be in the lab too long, is how fast is that reaction compared to when you were just doing these reactions with benzene? And so let's take toluene as an example. We're going to do the nitration of toluene because the nitration EAS is one of the faster reactions because it has such a strong electrophile involved in that reaction. But remember, we're focusing on the toluene identity, that is to say the methyl group, what it is and how it affects the reaction. It doesn't matter that you're doing a nitration or any other reaction. The change that happens to the benzene ring compared to toluene is based on the fact that toluene is a benzene ring that has a methyl group on it. Now, what the methyl group does, and I tried to find a picture that showed this, but it's a very subtle effect for the methyl group compared to other similar groups that are known as electron donating groups. But what the methyl group does is it donates electron density to the ring. We've actually already talked about alkyl groups doing this when we talked about the Birch reduction. We identify things as electron donating groups in that case as well, alkyl groups being one of those. It's also the reason why alkyl chains connected to carbon stabilize carbocations, because they donate electron density into that carbocation, into that positive charge. So now, what happens then if you're donating electron density into the ring? Well, that means there's more electrons in the ring itself. And if you remember from our discussions about EAS, the ring is the nucleophile. The benzene ring is the nucleophile in the reaction, in the mechanism. So the more electron density there is on the nucleophile, the stronger and the more nucleophilic that nucleophile is going to be. So that speeds it up, makes it go faster. So the other question about where does the next group end up, the regioselectivity, so to speak, of the product, has to do a lot to do with how the attached group affects the ring. Either before, we'll see some cases you can show it before, but oftentimes you see it specifically in the sigma complex intermediate. Remember this is generally a two-step process, and there's that sigma complex that has resonance. We're going to see when you look at that resonance, you can observe how these groups are affecting. How the toluene is affecting the determination of where the next group goes. So when we do an experiment, we observe that the ortho position is 63% of the product that forms, the meta is 3%, and the para is 34%. So between the three, the two most dominant are the ortho and para, pretty significantly compared to meta. And so that is what we find, and we'll see this again in the summary slide, is for the most part, activating groups, in fact, I believe all activating groups are ortho-para directors. They will always direct ortho-para and not meta. Now, why is that? So generally speaking, when we're talking about product determination, we're going to be looking at the mechanism. And it could be something like sterics, or it could be something energetic-wise having to do with the electronic structure. And here it has a lot to do with the electronic structure. The intermediate in this two-step process, generally two-step process of these EAS reactions, is that sigma complex. And in that complex, there is a positive carbocation that's resonating around the formerly benzene ring. Now, if you look at the three cases, an ortho attack, a meta attack, and a para attack, and you look then at the carbocation sigma complex intermediates, what you'll observe is for the meta attack, that positive charge as it resonates around the ring is never next to the toluene group. And so it never gets any benefit from the attached toluene group in that scenario. However, in the ortho attack and the para attack scenarios, both of those scenarios, if you look at their sigma complex, there is a resonance form in which the positive charge is located on a carbon next to that group. And remember that group, the methyl group, for example, in this case, is an electron donor. So it's able to donate electron density into the carbocation, stabilizing it. And thus, if you remember Hammond's postulate back in No Chem 1, what determines the rate and thus the favorability of a pathway is the activation barrier transition state, and that the energy, how energetic or how high in energy it is, and the energy or the way that transition state behaves is based on either the product or the the reactant or the product in that step, whichever one is closest in energy. So if you look at all these examples, it's always the carbocation intermediate or the sigma complex that's closest in energy to that transition state. So however those structures relatively are stable relative to each other, that is going to be observed in the transition state, and thus it's going to affect the rate and favorability of that pathway. And so since the ortho and para intermediates are stabilized in their structure, and it's as is observed in the resonance, those pathways are more favorable because the kinetics is stabilized, the transition state is stabilized. The meta is left, it's not unstable or destabilized, but it just doesn't gain the benefit. Now, you might wonder why the ortho is so dominant compared to para. When you kind of look, there's actually a little bit less stability in the ortho compared to the para. Now, the reason why the ortho still ends up having more is because the methyl group's really small, and there is 2 ortho positions that can be attacked relative to 1 para position. Now, you could ask, well, there's 2 metas. Why isn't that greater than para? And that's because the meta position still has a much greater activation barrier to go that pathway, and thus the energetics is too much to overcome. Statistics can only play a role when they're closer in energy, different pathways, when they're close in energy. So the statistics is really the issue here when it comes to ortho versus para in small groups like this. Now, methoxy groups, they are actually 400 times more reactive, or I should say a methoxy group on a benzene ring known as anisole activates the ring 400 times more than benzene. The reason for that is it is, once again, an electron donating group. And in this case, it donates via resonance. And so even before the sigma complex, you can actually see via resonance that the ortho and para positions have a buildup of a negative lone pair charge in their resonance forms. So ortho, para, ortho throughout the resonance, as we see here. So even before the sigma complex, there's already a buildup of electron density at those carbons. So not only will we see the sigma complex is stabilized via resonance, we already see there's a buildup of electron density at those specific carbons, helping even further along that activation aspect too, speeding them up. So these are strong activating groups, we'll find. In fact, they're so strong that you don't even need a catalyst for EAS bromination to occur. And it actually even is hard to stop it from doing just a single, it's hard to stop it from doing polybromination. Now, Once again, look at the percentages. It's 31% ortho, 67% para, 2% meta. Once again, ortho para, we don't usually separate those. For the most part, you can usually get away with saying both ortho para as the major products. But as you can see here, the ortho position is now a little bit minor compared to the para. The para is a little bit major in this case. And the reason is as soon as you start to get a little bit bigger than a methyl group, you start to create steric hindrance to the ortho position. So this methyl group dangling off to the side here starts to sterically hinder the ortho position compared to the para that's just completely on the other side of the ring. And when it comes down to just the energetics now, both the ortho and para electronically have that same stabilizing effect. That is, they have extra stabilization via resonance in their sigma complex compared to the meta approach or meta attack on the benzene ring. And remember, it's meta relative to the methoxy group. And thus, once again, you have a great stabilizing effect occurring in the ortho and para positions, whereas the meta position, it's not destabilized, but in this case, it's just not, it doesn't gain any benefit from the attached methoxy group. It still is fast in some degree, probably relative to benzene, but that position still isn't favorable. Now, the nitro group is an example of a deactivating group, and that's because it's electron withdrawing. It removes electron density. It withdraws it. There's two ways. It withdraws it via induction, that is to say, because it's an electronegative atom, it draws the electron density away from the ring. Also, not even just because, as we'll see, nitrogens that have lone pairs on them are actually electron donating groups. This nitrogen doesn't even have a lone pair that can donate it via resonance. It has no lone pairs on it, and in fact, it has a positive charge on it. So that positive charge and the fact that nitrogen is a little bit more electronegative than carbon, that draws the electron density out. It's a great inductive effect. And via resonance, it actually shows before any kind of attack, just the molecule sitting there, it shows via resonance that instead of with like methoxy, where there was a buildup of a lone pair and negative charge at the ortho-para position, there is actually now an electron deficiency at the ortho and para position via resonance. And so that shows that it deactivates the ortho and para position specifically. And so that's what we see. When you give it enough time for a nitro group to undergo another nitration event, we find that it is 93% meta and only 6% ortho and 1% para. And you do have to give it a lot of time because it's 100,000 times slower than just benzene undergoing nitration. And that's because of the deactivation effect of the nitro group. So once again, this is just, you might be, don't get confused, what's, so much stuff coming at you. This is just another way to prove it. So you can talk about why it's ortho-para directing and why it's deactivating by looking at the resonance before the reaction begins. But you can also take each scenario, the ortho attack, the meta attack, and the para attack, draw the sigma complex resonances for each of those scenarios, and observe the following. With the meta attack, once again, that positive charge resonates around the ring and is never next to the attached initial group, in this case, the initial nitro group. However, in the ortho attack and the para attack, via resonance, that positive charge in one of those resonance forms is next to the nitro group. Now, in the case of methyl, that was a good thing, or in the case of methoxy. However, in this case, being next to the nitro group means that that positive charge is next to an atom that is itself positively charged. As we saw earlier, the nitrogen is positively charged, and that puts two positive charges right next to each other, which is an unfavorable thing. Like charges repel each other, which is an energetically unfavorable scenario to have two like charges close together. So that destabilizes the ortho and para intermediates. So as we can see, they have a higher activation barrier. They're a less stable pathway. Whereas the meta product, its pathway, it's not necessarily stabilized, relative to the benzene ring, but it doesn't have the negative destabilizing effect that's found in the resonance structures of the ortho attack pathway and the para attack pathway and its sigma complex resonance forms. So it essentially is left alone again, but in this case, that's a good thing because not being left alone by that nitro group means destabilization for the ortho and para. So to sum this all up, and then we'll do one last exception, which is the halogens. To sum it all up, all electron donating groups are ortho-para directors. So as you familiarize yourself with electron donating groups, they are ortho-para directors. The electron withdrawing groups are meta-directors. The only exception is the halogens. As we're going to find, halogens are electron withdrawing groups, and thus they deactivate. However, they are ortho-para directors. So now let's take a look at the halogens, and they're that exception. So in the case of a halogen group being attached to a benzene ring, take chlorine, for example. Chlorine atoms are electronegative atoms, so they compared to carbon, and so they have an electron withdrawing effect. So via induction, they do withdraw electron density out of the benzene ring. And so that is expressed in the rate of the reaction. It is deactivated, it is slower, it is a slower reaction. You start attaching multiple halogens, you start deactivating that ring to a point, as we've talked in previous lectures, where certain EAS reactions won't even take place because it's too deactivated. However, halogen groups, when they're on a benzene ring, they direct, that is to say, when you do give them enough time to react, they will direct their product or that substitution event to occur at the ortho-para direction position still. And that's because even though they do withdraw electron density, they still have a resonance form that shows that there is an excess amount of electron density via resonance at the ortho and para position, as you can see right here. Ortho, para, ortho. So there's this weird competing situation where the halogen atoms draw electron density out due to the electronegativity of the atom, but via resonance, they do show that the ortho and para positions have a little bit more electron density via resonance than the meta position. And we can see the same effect happening here with the sigma complex intermediates when you look at the ortho attack, meta attack, and para attack. Now, once again, with the ortho attack and para attack, the sigma complexes show that there's a stabilization via an extra resonance form that occurs for them with the chlorine being attached. Whereas in the meta attack, that pathway, when you look at its sigma complex intermediate, it doesn't have that stabilization. Once again, it's not that the meta is destabilized, but rather the ortho and para have some extra stabilization in their sigma complex intermediate. So there's your introduction to how the various substituents that are attached to a benzene ring can affect the regioselectivity and also the kinetics or rate of the subsequent electrophilic aromatic substitution events. I'll see you in class.